All right, welcome to the Explainer. Today, we're going to break down this invisible force that's, well, it's at work all around us. It's the very thing that makes our electronics work, but it's also why they get warm. Yep, we're talking about electrical resistance.
Okay, so let's just jump right in with something I'm sure you've noticed. You plug in your phone, right? And after a bit, that little charger block is warm, sometimes even hot. Why is that? Ever really stop to think about it?
Well, the short answer? It's basically electrical friction. Seriously, think about it like this. If you shove a heavy box across a carpet, what happens? Friction makes things heat up. It's the exact same idea with electricity. It takes real effort to push it through a wire, and that effort, that struggle, creates heat.
So this electrical friction has a real name, of course. And getting a grip on this one concept is, well, it's absolutely crucial if you want to understand how any electronics work. I'm talking everything from a simple light bulb all the way up to a supercomputer. So here it is, electrical resistance. And honestly, the name says it all. It's a measure of how much an object opposes or, well, resists the flow of electric current. It's literally pushing back, and we measure this pushback in a unit called the ohm.
Okay, now to really make this click, we're going to use a classic analogy. It's honestly one of the best ways to visualize what's going on inside a wire. So I want you to picture electricity, like water flowing through a pipe. Got it? Okay, so voltage, that's the water pressure. It's the force pushing the water forward. The current, that's the actual flow rate, how much water is actually moving. And resistance, well, that's the clog. It's anything that gets in the way and slows things down. A narrow section of pipe, a bunch of gunk, you get the idea. And this is super intuitive, right? If you've got a clog and you still need to get the same amount of water through, what do? You crank up the pressure. It's the exact same thing with electricity. If you have high resistance, you need higher electrical pressure, a higher voltage, to force the same amount of current through. All right, so if resistance is the clog in the pipe, that begs the question, what determines how big the clog is? Let's dive into what actually makes something a good conductor or a bad one. And it really just boils down to two key things. First up is the material itself. I mean, it's obvious that copper is going to behave differently than, say, rubber, right? And the second thing is its geometry. We're talking its physical size and shape. Let's go back to the water pipes. Imagine trying to drink a thick milkshake. Is it easier to use a long, skinny coffee stirrer or a short, wide straw? The coffee stirrer, right? It's a struggle. It's the exact same principle here. A long, thin wire makes it way harder for the current to get through. That means high resistant. On the flip side, a short, thick wire is like a 6-lane superhighway. The current can just cruise right through with almost nothing in its way. That's low resistance. And that, by the way, is why thick copper wires are such fantastic conductors. So for a whole lot of materials, this relationship between voltage, current, and resistance is super simple and predictable. Like if you double the voltage, you get exactly double the current. It's this elegant, straightforward relationship that's a cornerstone of all electronics. It's called Ohm's law. And any material that plays by this rule, we call it ohmic. And check out the numbers here, because the range is just wild. A meter of copper wire, practically zero resistance. The tiny filament in an old light bulb, hundreds, maybe even 1,000 ohms. And then there's us, the human body. When we're dry, we can have a resistance of up to 100,000 ohms. The scale here is just massive. But you know how it goes in science, right? For every great rule, there are always some really interesting exceptions. And when it comes to Ohm's law, the rule breakers are where things get really cool. Look, Ohm's law is a fantastic rule of thumb. For basic stuff like simple wires or those little resistor components you see on a circuit board, it works perfectly. For a huge chunk of electronics, it's all you need. But then you run into what we call non-ohmic materials. And with these guys, the resistance isn't a fixed number. Nope, it's a moving target. It actually changes depending on how much voltage or current you're pushing through it. And don't think these are some weird, exotic things you'd only find in a lab. We're talking about super common parts. Diodes, which are basically one-way streets for electricity, batteries, transistors, even the filament in an old-school light bulb. Its resistance changes as it heats up. None of them follow Ohm's law perfectly. And then there's the ultimate rule breaker, the one that throws the whole idea of resistance out the window: superconductivity.
We're not just talking low resistance here. We are talking zero. Absolutely, perfectly zero resistance. A completely frictionless superhighway for electricity. Okay, just stop and think about what that really means for a second. Zero resistance means zero friction, zero wasted energy, zero heat. So if you take a closed loop of a superconductor and get a current flowing in it, it just keeps going. Forever. With no power source, no battery, the current just flows and flows, endlessly.
So, okay, this is all cool science, but why does it matter in the real world? Well, it matters because learning how to manage resistance, how to control it, use it, or get rid of it, is fundamental to basically all of our technology.
Let's go all the way back to the beginning. Remember that warm phone charger? Well, that effect has a name. It's called Joule heating. It's this simple, direct conversion of electrical energy into heat that happens anytime a current has to struggle its way through a resistor.
And this is where you see the two faces of resistance. Sometimes it's the enemy. Think about all the energy that's just lost as heat in the big power lines that stretch across the country. That's a huge waste. But other times, it's our best friend. We've learned how to harness it. That exact same Joule heating effect is how your toaster toasts, how an electric stove cooks, and how an old light bulb glows. We are using resistance on purpose.
So when you boil it all down, it's all about control. Whether you're trying to design a tiny light bulb filament that gets white hot, or a massive superconducting magnet for an MRI machine that needs to be perfectly efficient, the game is the same. How do you manage the flow? Understanding resistance is what gives us the power to play that game, to either fight it and get rid of it for ultimate efficiency, or to embrace it and crank it up to generate the heat and light that our entire world runs on.